Hi, and welcome to the third in a six-part series explaining how to quickly deploy a powerful, fast, and scalable data analytics solution using the free components of the Elastic Stack. If you haven't already watched the previous video, I encourage you to do so first. In this video, we'll examine some simple Python scripts I've written to do the ETL, that's extract, transform, and load, of the climate data that we'll be using in our example. As discussed in the previous videos, we'll first insert the data into a MongoDB database so that we have a full-fledged database as our primary storage. We'll then index this data into Elasticsearch via a second script. We'll be using the data from the Global Historical Climatology Network's monthly release version 3. This contains a nice large dataset of 25 million objects that should illustrate the power of this stack, while still being small enough to run fine in my local Docker VM. If you're interested in setting up this example on your own, I have the scripts and instructions on my GitHub here. The data files I'll be using are available here. All you need to do is extract the two files that are contained in each of these zip files, as well as grab the country codes file. We'll put that all into a single folder next to our code. Alright, now we'll briefly look over the scripts. The first we'll look at is responsible for populating MongoDB and is called ghcn to mongo.py. This is just a simple script for demo purposes and lacks the flexibility such as a command line interface that you'd want in a more mission critical script. I'm going to go over it quickly since most of the code is focused on parsing the ghcn data files, and the details of that isn't really the focus of this series. So as I mentioned before, we've extracted and stored those files from the ghcn FTP server in a data folder next to our scripts. And then here we're going to tell it where to find it, and then set up some connection info for our MongoDB database, which we've already set up in the previous video. The rest of these settings can mostly be left alone. So initially what we're going to do is we are going to iterate over all of the DAT files in that data folder. These are what contain the actual climate data that we're going to extract. So we'll print that we're processing it, and then we will also find the meta file that goes along with those. Then we'll create an instance of our ghcn to mongo class and run its run function. This is going to basically ingest each of these different data sets one by one in a loop. So the constructor of this ghcn to mongo class does some setup for us. So it initially loads in our data file and stores that to a private variable. It also gets countries and metadata, which are defined in these two functions. And these basically just know how to parse these two folders or files, the countries and the INV file. And then makes those basically available as a dictionary, which we can use to look up country information or metadata information as we're processing the actual data files. The first time we run this, we're going to call or set this argument first to true. And what that's going to do is basically reset the database from scratch. So this doesn't support any sort of incremental updating. It just does it all at once. And so it's expecting to start from scratch. And so this basically ensures that that happens every time we run this script. So once we have all that set up, we can run the run function. So the run function is basically just going to call process file, which is going to return a generator, or is a generator of objects, each of which is a separate temperature measurement that needs to be stored in our Mongo database. We're going to insert these in batches for performance reasons, and so we're going to maintain this little list of objects as called batch, and we'll build it up until it hits our batch size, which is configured in a constant at the top, and then insert that batch one at a time until we're done, at which point we insert whatever remains. So process file simply iterates over the lines in the data file and then calls transform on each of those. And then transform is what actually does the parsing of the data file. So we initially create a base object which contains some information that we look up from those country and meta dictionaries that we set up earlier. We store the element, which is like what type of measurement this is, and the values for that could be t-average, t-min, or t-max. And then we also set a special field that we define called ES_state, and we initialize it with a value of insert. And we'll talk about what this is for when we talk about the next script. But basically this is just telling our Elasticsearch synchronizer what state this object is in. Has it been synchronized yet, and what do I need to do with it? So then the rest of this is just pulling out information from these data lines and storing that into the appropriate fields in our object. Once we're done, we return we yield the object, which gets yielded from here, and then ultimately gets added to our batch. Okay, now it's time to index our Mongo collection into Elasticsearch. For this, I've written a simple ETL script that will periodically check Mongo for new or updated objects and then insert or update them in Elasticsearch. So let's review this code. Okay, once again, we have our Mongo connections information like on the other script, because we're going to have to connect to Mongo again. We also have our connection information for our Elasticsearch cluster and index. And then we have another class now called Mongo to Elasticsearch. And the init function of this basically sets up our Elasticsearch connection as well as our Mongo connection. It stores our index, which is the Elasticsearch destination, in a local variable. And it also calls setup index. And what that does is it creates a new index with the name that we've specified and sets some initial settings. And so what these settings do is they basically just define some mappings that we don't want Elasticsearch to determine on its own. So one of the things I mentioned earlier, which is a benefit of Elasticsearch, is that generally you don't have to predefine the fields in your data. It'll automatically generate the mappings for you as it sees those fields in the data coming along. And as long as your data types are consistent across all of your objects, that generally works fine. But there are a few cases where you need to be explicit about the type of mapping, and one example is the geopoint type. So this is basically telling Elasticsearch that stored in this meta location nested object is something that we're going to treat as a geopoint object. And that is basically just a latitude-longitude pair that Elasticsearch is going to treat specially. And what it enables is for us to do geographic plotting in Kibana. The other thing we're going to specify here is a refresh interval of 1 minute, and that's basically just a performance optimization to prevent the Elasticsearch index from completely refreshing every time we insert a new object, and to only do this every minute. Since we're batch loading data very quickly, we don't need it to be constantly refreshing and perfectly up to date. We just want it to be refreshing often enough that we can see progress without causing too much overhead. Okay. So when we run this script, we're basically just going to initialize our ETL object, and then we're going to start an infinite loop. And the reason this is an infinite loop is that this is going to monitor our collection for updates and for new data and automatically synchronize them into Elasticsearch. So it's going to keep running, and every time it finishes running or it stops finding new things to process, we're going to wait for a few seconds, and then we'll run again. So etl.run is going to be our main Mongo to Elastic ETL entry point. And as before, we're going to have a batch. We are going to figure out how many documents match our query. And this gets to what I talked about in the last script, which is this ESState field. So this is a special field that we have added to these objects. And we're basically handling a few different types or values for this field. Insert is going to indicate new objects that have not yet been added to Elasticsearch. Update is going to be an existing object that has not yet been added to Elasticsearch. And then remove is going to be an object that presumably is in Elasticsearch, but which we want to remove. So this is going to define a Mongo query, which is going to return any object that has any of those values. We're going to count how many objects that is, and we're going to use that in our TQDM progress bar so that it knows how much data we have to process, and it can accurately tell us how we're progressing. Then we're going to do a query against Mongo for all the data that's matching that query, and we're going to iterate over every single object. As before, we're going to add them to batches as we transform them, and then insert them in batches. And we'll also have to update the progress bar to tell it how far we've come along. So similarly to before, we have this transform function, and this is going to create our base Elasticsearch object, which is similar to what we have in Mongo, but it has a few different things. So first we have to define the index. We're going to tell it what the ID is, and we're going to set it to the same ID as Mongo. And that provides us a very easy way to trace from Elasticsearch back to the original object in Mongo. We're also going to give it a type, and that's defined in a constant up top. It doesn't really matter too much. Then we're going to delete from the object the Mongo object, the object ID, because we don't want to store that separately. We already have an ID now in our object. We're going to check to see if the state is delete, and if so, we're going to tell Elasticsearch that when it processes this object, it's going to delete the object. Otherwise, it's going to assume that it needs to be added. And one thing to know about Elasticsearch is there's no real distinction between adding something and updating it. If you're inserting something with an ID that already exists, it's just going to overwrite it. And that's actually really handy in our case because typically, since our source of truth is Mongo, we want Elasticsearch to reflect that no matter what. And so if we're processing an object that already exists in Elasticsearch and it's different in Mongo, we just want to overwrite it. We don't want to do any sort of fancy update operation that could end up with different values in Elasticsearch or Mongo. We want them to always be the same. So we'll delete the ES state because we don't really need that to be in our Elasticsearch object. And then we'll set source to object. So source is essentially just the contents of your indexed object in Elasticsearch. Then we'll return that and then add that to the batch. So insert batch is a little bit fancy. So the main responsibility of this is to just insert these objects into Elasticsearch. And that's achieved by this function call alone. So we're going to give it the connection we have to Elasticsearch that we set up earlier, and then we're going to pass in the batch. And this is a function provided by the Elasticsearch Python driver that allows us to do batch updates. It returns the result for every object that was inserted. And so we're going to pull these out, and we're going to pull out the object ID, and we're going to go through and now update Mongo to reflect what just happened. Because if we let Mongo stay the way it was, we would continue to reprocess the same objects all the time. We haven't touched the ES state field that said to insert this object. So we need to go back to Mongo and update it with the synchronization state of the object. And so what we're going to do is we're going to do another batch update of Mongo, and for every object that we just inserted or tried to insert into Elasticsearch, we're going to see if it was successful. We're going to create an update object for Mongo with the object ID, and we're going to set its state now to complete because it was successful, and we'll add that to our batch. If it was not successful, then we'll update the ES state to error, which will also prevent it from getting reprocessed, but will let us find out later with a simple Mongo query which objects did not end up synchronizing into Elasticsearch correctly. We'll create this Mongo batch, and then we will do a bulk write of those operations in Mongo. So that's it. Basically what this will do is it'll handle anytime you update or insert a new object into the Mongo collection, assuming you use these the appropriate ES state values, and it will make sure that those values or those objects are reflected in Elasticsearch. Otherwise, it will mark them as errored. So as you can see, this code has almost no knowledge of the data that we're storing in Mongo, and with the exception of that location mapping that tells Elasticsearch to treat that as a geolocation, which is technically separate from the ETL process itself, I haven't told Elasticsearch anything about my data either. Elasticsearch will automatically generate the mappings for new fields as it discovers them according to their type. The only gotcha here is, as I mentioned before, you can't have multiple mapping types for the same field, and you'll get insert failures if you try to insert a field value that can't convert into the existing mapping type. So for example, if you insert an object with a field of day whose value is 3 and type is a number, a subsequent attempt to insert an object with a value for day of Monday will fail. The reverse is also problematic. While you won't fail to insert a number into a field with a string mapping, it will be handled as a string, which means you won't be able to do any sort of numeric analysis on that field, such as averages. In general, this shouldn't be a problem since hopefully your Mongo objects fields will have consistent types across all of your objects, but it's something to watch out for. There's one really nice exception to this, and that's lists. The same field can contain a single value or a list of values, and Elasticsearch will handle it fine. Another thing I want to address is that this script is intended to be simple and easy to understand, but it's not necessarily the optimal approach if you're dealing with a ton of data. While I do use bulk inserts and updates to improve performance, there are likely faster approaches to this task. Options would include a bulk load and insert for the initial sync, and then tailing the Mongo oplog, which is Mongo's history of operations that is used to keep its replica sets in sync. This is faster and more real-time than the approach I use, and has the benefit of not requiring a special field and index in our Mongo objects to track the synchronization state of our objects. However, it's significantly more complicated, especially if your Mongo collection is sharded, so I'd only suggest going this route in more advanced cases. You might want to check out Mongo's Mongo connector for Elasticsearch, which uses this approach, but note that this project has not been kept up to date and lacks support for the latest versions of Mongo and Elasticsearch. You might also consider using Elastic's Logstash project to implement the ETL. So let's go ahead and run these scripts. I like to use a virtual environment, so we'll go ahead and activate that. and then we'll simply run our main ETL script. Alright, so we can see that that's running now. So in parallel, we can go ahead and start off our Mongo to Elastic synchronization script. We'll do that by simply running the Mongo to ES script. And we'll see that it's found 310,000 objects already in our Mongo collection, and it's starting to process them in. The last thing we'll do in this video is configure the index we just created and populated in Kibana. We'll have to wait a minute before we do this after starting the ETL because of our refresh interval. We won't be able to actually see the index and its data until at least a minute has passed. But once it has, we can go in here and set it up. So we'll go to the Management tab in Kibana, click on Index Patterns, and it'll show us the indexes that already exist that we can choose from. And we're going to go ahead and pick this one. This is an older one that I had already done. Then we'll click Next Step, and we'll choose our date column if we have one, or date field. You don't have to have a date field to use Kibana, but for a lot of features you need one, and definitely if you have a date in your data, you should select that here. So now it'll show all the fields in the index that is detected so far. Something to note is that this list does not auto-refresh, so if new fields are added to your index over time as you ingest new data, you will need to refresh this field periodically. Also note that there are some configurable limits to how many fields can realistically exist in your index. I've found that for best results you should try to have no more than around 1,000 fields in your index, although this isn't a hard limit and there are things you can do to optimize the index to handle more, such as turning off indexing for fields that you don't need to search. Another thing we'll do over here is create a scripted field. These let you add synthetic fields to your index which get generated at query time, and which let you clean up or modify data from your objects to make analysis easier. A good use of these in our case is to have an additional temp field that has the Fahrenheit temperature. We can create that as follows. We'll call this tempf. We're going to use the default language of Painless, which is a proprietary language similar to Java that exists specifically for creating scripted fields. We're going to leave it at number. We'll pick a number as the format, and we'll leave the default pattern here. And then we'll scroll down and add a script. Now they have documentation on how to write Painless scripts, but suffice it to say for this, we basically just want to pull out the temp field from our data, and then with its value we're going to apply the conversion math to turn it into Fahrenheit. And with that we can save this. Alright, one more thing we'll do while we're in the management interface is go to Advanced Settings, and we're going to change the default time picker interval from the default of 15 minutes. In our case, our data spans over 150 years, and so this default doesn't really make sense. So we'll make it 150 years, and then we'll go to the Discover page and see what our data looks like. So our data is still ingesting, so there will be more to come, but we can go ahead and verify that there is indeed data. We can look at it, make sure it looks like we expect, and we can also verify that we have our scripted field here now, and we can add those as columns and verify that, here's the Fahrenheit equivalent of these Celsius temperatures. Alright, so now that we have our data in our Elasticsearch index, it's time for the fun part, exploring and analyzing the data in Kibana. For that, check out the next video.